There's a comfortable assumption people carry around about technology. The further back you go in history, the more primitive things get. People in the past had simpler tools, less knowledge, fewer materials. They got by, but they couldn't do what we do now. That story works as a rough sketch most of the time. There's a lot more electricity, computing power, and chemistry available to a modern engineer than to a Roman or a medieval craftsman. The problem is that the rough sketch leaves things out. There are a handful of inventions, processes, and finished objects from the ancient and pre-industrial world that modern engineers still can't fully reproduce. Not because the technology was magic, because the people who knew how to do it died, or were killed, or simply stopped passing the knowledge along, and the trail went cold before anyone wrote it all down. Some of what follows has been partially reverse engineered. Some has been studied for decades without producing a working modern equivalent. In every case, there's a finished object or a documented process sitting in front of researchers, and the path from observation to replication has turned out to be harder than anyone expected. Here are 10 examples. Number 1. Roman concrete. The Pantheon in Rome has a domed concrete roof that's still intact almost 2,000 years after it was built. It's the largest unreinforced concrete dome in the world. Modern concrete buildings, designed and built in the last 70 years, often start cracking within a few decades. Many of them are already being torn down and replaced. A Roman dome built in 126 AD is fine. Out on the coast, the Romans built harbors and breakwaters using a concrete mix that sat directly in seawater. That concrete should, by modern logic, have been falling apart for 2 millennia. Instead, when researchers tested it in the 2000s, they found the opposite was happening. The Roman concrete had been getting stronger over time. The salt water reacted with volcanic ash in the mix to grow a rare mineral called aluminous dobermarite, plus crystals of philipsite. In the cracks, the concrete healed itself. Modern Portland cement does nothing like that. It corrodes when exposed to salt water, which is why concrete piers built in the 1960s look worse than Roman ones built before Jesus was born. We've identified some of the chemistry now. We know about the volcanic ash, the lime, the seawater interaction. We've even isolated a specific ingredient called lime clasts, which act like tiny reservoirs of calcium that release into water and trigger new mineral growth when cracks form. A 2023 paper from MIT actually showed this mechanism in detail. What we haven't fully reproduced is the long-term performance. Modern attempts to make Roman-style concrete work in the lab, but no one has built a structure with it and watched it hold up for centuries, because nobody has centuries to wait. There's also the issue of practicality. The volcanic ash the Romans used came from specific sources in central Italy. Scaling Roman concrete up to modern construction volumes would require either finding equivalent volcanic deposits worldwide or engineering substitutes, neither of which has been done at industrial scale. Number 2. Damascus steel. From around the 3rd century until the 17th, blacksmiths in the Middle East were forging sword blades out of a material that became almost legendary. The blades had a flowing, watery pattern across their surface. They held an edge that, by reputation, could cut through other swords. The steel was made from imported ingots called woots, smelted in southern India, and traded north into Persia and Syria. The woots itself was a high-carbon crucible steel, produced in clay containers heated in charcoal furnaces, and the specific impurities in the ore turned out to matter as much as the smelting technique. The smiths who worked it kept their methods secret, passing the knowledge down through families and small workshops. By the late 1700s, the supply of woots dried up, the workshops closed, and the technique faded out within about a generation. Modern researchers studied surviving Damascus blades with electron microscopes and found something strange embedded in the steel. Carbon nanotubes and nanowires, formed by the specific way the iron interacted with trace impurities during forging. The smiths had been producing nanoscale structures inside their blades without any concept of what a molecule was, let alone a nanotube. We can make modern steel that's harder, stronger, and more reliable. What we can't do is reproduce the exact internal microstructure of an authentic Damascus blade. The original blades performed at a level that combined hardness with flexibility in a way modern alloys still struggle to match. There are reasonable theories about how it was done. There are workable imitations called pattern-welded steel that look similar. The genuine article made by the lost technique is something nobody has put together end-to-end in over 200 years. Some researchers have come close, especially Bulat steel reconstructions developed in Russia in the 19th century. But the original Damascus methodology, with all its specific impurity patterns and forging temperatures, hasn't been fully recovered. Number 3. Greek fire. The Byzantine Empire had a secret weapon. They called it sea fire, liquid fire, or in some sources just the fire. It was a flammable liquid that could be sprayed from siphons mounted on ships, and once it hit a target, it kept burning. Water didn't put it out. In several recorded engagements, including the defense of Constantinople against Arab fleets in the 7th and 8th centuries, Greek fire turned the tide of battle. The emperors guarded the formula obsessively. It was held by a small group of imperial engineers, passed only to trusted family members, and never written down in full anywhere a researcher has found. The Byzantine Emperor Constantine VII, writing in the 10th century, told his son that the recipe had been delivered to the first Christian emperor by an angel, and that anyone who shared it with foreigners would be struck dead by lightning. That was the official line. The practical reason was strategic. As long as only Byzantines knew how to make Greek fire, Byzantine ships could destroy enemy fleets at will, and the empire's enemies had no way to retaliate in kind. By the 13th century, references to Greek fire stop appearing in Byzantine military texts. Whatever the secret was, it died with the last people who knew it. Modern chemists have proposed reconstructions. Some involve naphtha, quicklime and pine resin. Others throw in saltpeter or sulfur. The closest modern equivalents are napalm and other gel incendiaries, which produce similar effects, but the actual Byzantine formula remains a guess. Nobody has produced a substance that does exactly what the Byzantine sources describe, which is to spray as a stream, ignite on contact, and continue burning across the surface of seawater. The Byzantine accounts also mention that Greek fire could be launched from hand-thrown grenades and from siege catapults, suggesting the underlying mixture was versatile enough to work in multiple delivery systems. Whatever it was, it didn't survive the fall of Constantinople, and the institutional knowledge that allowed its production simply disappeared. Number 4. The Antikythera mechanism. In 1901, sponge divers off the coast of a small Greek island called Antikythera pulled up a corroded lump of metal from a Roman-era shipwreck. The lump turned out to contain dozens of bronze gears, dials and pointers, all packed into a wooden case about the size of a shoebox. The device was dated to around 100 BC, give or take a few decades. It was a calculator. Specifically, it was an analog computer for predicting astronomical events. The user could turn a hand crank, and the gears inside would track the positions of the sun, the moon, and the 5 planets known to the ancients. It calculated lunar phases, predicted solar and lunar eclipses, and tracked the cycles of athletic games like the Olympics. The gear ratios were sophisticated, including the first known use of a differential gear, which wouldn't appear in European clockwork for another 1500 years. Researchers have spent over a century studying the corroded remains. Through X-ray tomography, computer modeling, and painstaking reverse engineering, they've reconstructed how it probably worked. Several modern replicas exist, but the level of precision needed to make the original gears, with hand tools, in 100 BC is something that working machinists still find baffling. The teeth on some of those gears are spaced within tolerances that would be hard to achieve today without a milling machine. Nothing else from that era is even close. No other ancient mechanism has been found that uses gears with this kind of accuracy. The technology seems to have appeared, been used, and disappeared without spawning a tradition of similar devices. Whoever built the mechanism, whoever taught them, and whoever might have built more of them, all left the historical record without a trail. The first device of comparable complexity in the surviving record is from medieval Islamic engineering more than 1,000 years later. Number 5. Roman flexible glass. The Romans had glass makers across the empire, producing everything from simple bottles to elaborate cut glass tableware. According to several Roman writers, including Pliny the Elder, Petronius, and Dio Cassius, one of those craftsmen invented something different, a bowl that, when dropped on a hard floor, dented like metal instead of shattering. The craftsman then took out a small hammer and tapped the dent back into shape. The Roman accounts say that he brought his invention to the Emperor Tiberius, expecting reward. Tiberius, according to the story, instead had the man executed and his workshop destroyed. The justification given in various versions of the story is that flexible glass would have devalued gold and silver, since unbreakable glassware could replace metal cups and vessels and disrupt the precious metals economy. Most historians treat this story as legend, partly because no physical example of vitrum flexile has ever turned up in the archaeological record. Some researchers, including modern materials scientists, have argued that something resembling flexible glass could theoretically have been made with Roman-era materials, possibly using boron-based glasses or early forms of polymer compounds derived from plant resins. Nobody knows what the Roman craftsman actually made, or whether he made anything at all. If the story is true, the technology was deliberately killed before it could spread. If it's not, it's still one of the strangest examples in history of a society that may have invented something and then chose to destroy it. Number 6. The Stradivarius violin. Antonio Stradivari, working in Cremona, Italy, between roughly 1666 and 1737, built around 1,000 stringed instruments. Several hundred of them survive. His violins are widely considered among the best ever made, with a sound that violinists describe as warmer, brighter, and more responsive than modern instruments, costing many times less. They sell for millions of dollars when one comes to auction. The thing is, modern luthiers have studied every aspect of these violins: the wood, the varnish, the shape of the bridges, the thickness of the front and back plates. They've measured everything with CT scans, chemical analysis, and frequency response tests. And while modern instrument makers can build excellent violins, they can't consistently produce the specific tonal qualities of a Stradivarius. Several theories try to explain why. One suggests the wood was unusually dense because of a cold period called the Little Ice Age, which caused slower tree growth and tighter grain. Another points to a chemical bath the wood may have been treated in before construction, possibly using fungal cultures or borax compounds that altered the cellular structure of the wood. A third focuses on the specific varnish Stradivari mixed himself, the recipe for which is not fully known. Probably all of these factors contributed. The combination, though, is something nobody has cracked. Blind tests where professional violinists play modern and Stradivarius instruments produce mixed results, with the experts often unable to tell them apart in some settings. In other settings, the Stradivarius stands out. The pattern is consistent enough that something real is happening even if we don't fully understand what it is. Adding to the difficulty, Stradivari and his contemporaries in Cremona, including the Guarneri and Amati families, all produced instruments of comparable quality. So whatever was happening in that one city in that one century wasn't a single craftsman's secret. It was a broader tradition that died with the generation that practiced it. Number 7. Maya blue pigment. The ancient Maya, working in Central America between roughly 600 and 1500 AD, produced a paint pigment of an unusually bright, stable sky blue color. They used it on murals, pottery, and ritual objects. They also painted sacrificial victims with it before throwing them into sacred sinkholes called cenotes. The pigment is still vivid on Maya, sites that have been exposed to centuries of sun, humidity, salt air, and acid rain. Most pigments fade or break down under those conditions. Maya blue doesn't. Chemists in the 20th century figured out the general composition. It's a mix of indigo dye, derived from a local plant, combined with a particular clay called palygorskite. What's strange is how the two are bonded together. The indigo molecules slip into the channels and pores of the clay and lock there at a chemical level, creating a hybrid pigment that's much more durable than either ingredient alone. Researchers have been able to make modern versions in laboratories. The exact preparation method the Maya used, though, isn't fully understood. There seems to have been a heat treatment involved, probably over copal incense fires, that bonded the two materials. Reproducing the original quality, with the same stability and shade, has turned out to be harder than it looks. The pigment was important enough to the Maya that they had specific religious associations with it. The recipe wasn't written down. When the culture collapsed in the centuries after Spanish contact, the knowledge of how to make it disappeared with the artisans who knew the steps. Number 8. The Iron Pillar of Delhi. In the courtyard of an old mosque complex in Delhi, India, stands a slender iron pillar about 23 feet tall. It was made around 400 AD during the Gupta Empire. The pillar weighs roughly 6 tons. It's been sitting outside, exposed to monsoons, dry heat, and salt air for over 1600 years. It should be a pile of rust. It isn't. The surface has a thin protective layer of iron oxides that has prevented serious corrosion across all that time. Modern metallurgists have studied the pillar and identified what's happening. The iron contains a high phosphorus content, which formed a passive layer of miserite, a particular iron phosphate compound that protects the metal underneath. The smiths who forged it managed this without modern chemistry, by using iron ore that happened to have the right impurities, and by working the metal in a way that left those impurities concentrated at the surface. The technique was lost when the empire fell, and India's later iron-making traditions didn't preserve it. There are smaller iron objects from the same period that show similar properties, suggesting the technique was used elsewhere. But the Delhi pillar is by far the most dramatic example. Modern iron of equivalent purity can be made today, but not with the same self-protective surface chemistry produced by the original smiths. We can probably reverse engineer something equivalent. Nobody has bothered because we have stainless steel for the same purpose. The point is that nobody has actually replicated the original. Number 9. The Lycurgus Cup. Sitting in the British Museum is a Roman glass goblet from the 4th century AD. When light hits it from the front, the glass looks jade green. When light shines through it from behind, the same glass turns deep red. The effect is striking enough that visitors usually assume there's some kind of trick involved. There isn't. The color shift is built into the glass itself. What's happening inside the cup is that the Roman glassmakers, working 1600 years ago, added tiny particles of gold and silver to the glass mixture. The particles are about 50 nanometers across, which is too small to see with any optical microscope. They interact with light in a specific way that changes the apparent color based on the direction the light is coming from. This is, by any normal definition, an early example of nanotechnology. The Roman craftsmen who made the cup almost certainly didn't understand what they were doing at a molecular level. They probably knew that adding small amounts of certain metals to glass produced specific color effects, and they may have followed a recipe handed down through their workshop. Modern nanotechnology has produced similar dichroic effects in laboratories, using carefully controlled metallic nanoparticles. Reproducing the Lycurgus cup exactly with Roman-era materials and methods isn't something anyone has fully managed. The cup is one of a kind. No other example of this specific dichroic technique has been found from the period, which suggests the technique was rare even in its own time, possibly the work of a single workshop or a single craftsman whose method died with him. Number 10. The precision stonework of the Great Pyramid. The pyramids of Giza were built between roughly 2600 and 2500 BC. The Great Pyramid, the largest of them, contains around 2.5 million blocks of stone, ranging from about 2 tons to 50 tons each. They were cut, transported, lifted into place, and fitted together with joints so tight that in some sections you can't slide a sheet of paper between adjacent blocks. That precision is the part nobody has fully figured out. The Egyptians had copper tools, ramps, water leveling, and a lot of organized labor. We know roughly how they quarried stone, how they moved it on sleds across the desert, and how they probably raised it. What's harder to explain is the consistency. The interior chambers of the Great Pyramid, especially the granite blocks of the King's Chamber, show surface finishes and angle accuracies that would be hard to produce today without diamond-tipped power tools. Some of the cuts are almost optically flat. The blocks are square within a few millimeters across surfaces that are dozens of feet long. Modern stoneworkers have tried to reproduce the same finishes using only Bronze Age tools and gotten close but never quite there, and never at the scale or volume the Egyptians produced. The standard answer is that the Egyptians had developed specific techniques like abrasion with sand slurries and copper saws that were refined over centuries and don't translate well to short-term reconstructions. Some specific operations, like drilling through hard granite, still produce results in ancient examples that experimental archaeology hasn't fully matched. The full toolkit, the full repertoire of methods, didn't survive in usable form. We have the pyramids. We don't have a working manual for building one. Each of these examples has something in common. The technology was real. The objects are still here, sitting in museums or standing in old cities, waiting for someone to figure them out. The people who knew how to make them died or were killed, or stopped training apprentices, or simply ran out of the raw materials they depended on. The knowledge wasn't written down in enough detail to recover. And so, despite living in a century with electron microscopes and computer modeling and global manufacturing supply chains, we're still working backward from the finished products of cultures that have been gone for 1,000 or 2,000 years. That doesn't mean the modern world is technologically inferior. Modern technology can do things ancient cultures couldn't dream of: microchips, antibiotics, satellites, machine learning. The list is long. What it means is that knowledge can be lost. Specific, valuable, hard-won knowledge, the kind that takes generations to develop, can disappear in a single generation if the right people stop teaching the right students. Every craft tradition that goes extinct takes a piece of the human record with it. Part of the reason is how knowledge actually gets transmitted. Most of what a skilled craftsperson knows isn't written down. It's stored in their hands and their reflexes and their habits, accumulated through years of trial and error. They might write down a recipe or a procedure, but the small adjustments, the way they read the color of molten metal or the smell of curing varnish, those things sit in their head. When they die without a fully trained successor, that part of the knowledge dies too. The recipe survives. The skill behind it doesn't. Some of these examples may eventually be cracked. Roman concrete is closer to being reverse engineered than it was 20 years ago. The Antikythera mechanism is now understood at the level of its mathematics, if not its precise manufacturing methods. There are research programs at major universities working on Damascus steel, on Maya blue, on the chemistry of historical varnishes. Others may stay mysterious. The Roman glassmaker who allegedly invented flexible glass is dead. So is the Byzantine engineer who knew the Greek fire recipe. So are the Maya artisans who made the blue pigment, the Indian smiths who forged the Delhi pillar, the Italian luthier who built the violins. We have what they made, we don't have them. That's the part of the past that's harder to recover than any artifact. And it's worth thinking about what that means for the present. Right now, in workshops and laboratories around the world, there are people who hold specialized knowledge that isn't written down anywhere. Specific welding techniques, specific glass blowing methods, specific recipes for restoration materials, all of them sitting in the heads of people in their 60s and 70s. If those people don't pass it on, in 20 years there will be a list of modern lost technologies, not many, but some, the same way it has always happened.